Hello everyone, this is Yashveen from Exam Help Web. In this video, I'll be solving Paper 4 Variant 3, May June 2016 IGCSE Physics. Question 1. State why force is a vector quantity. Force is a vector quantity because it has both magnitude and direction. B. A 20 Newton force and a 15 Newton force act at the same time on an object of mass 14 kg. Calculate the maximum possible force on the object due to these two forces. So an object would experience maximum force when both of the forces are acting in the same direction. So that means you'll have to add up 20 and 50 newtons of force, which will be 35 newtons, to the acceleration caused by a resultant force equal to this maximum force. So the resultant force is equal to mass into acceleration, which means acceleration is the resultant force divided by the mass that it's acting on, and this will be 35 divided by 14 kg mentioned in the question, and this will be 2.5 meters per second squared. C. Figure 1.1 shows a river in which the velocity of the flowing water is 0.85 meters per second parallel to the river banks. So here you've got the velocity of water. A swimmer sets off from one bank. The velocity of the swimmer relative to the water is 1.2 meters per second at 45 degrees to the river banks as shown in figure 1.1. So the water flows in this particular direction and the swimmer goes in this direction with an angle of 45 degrees to the velocity of water. In the space below, draw a scale diagram to determine the resultant velocity of the swimmer relative to the river banks. This velocity is the resultant of the two velocities shown on figure 1.1. Label this resultant on your diagram. So just to give a brief idea of drawing vector diagrams, when you are given with two vectors and there's a resultant vector, like in this case it is going to be the resultant velocity, you start with a vector, any of the two, and then you draw the second vector by connecting the tail of the second vector to the head of the first vector, so that way, and then you will connect the tail of the first vector to the head of the second vector to get the resultant. So here you've got the resultant, and so in this case the first step you need to do is you set out your scale. I've chosen a scale of 1 centimeter for every 0.1 meters per second of a speed, and that means for 0.85 meters per second of speed I'd need to draw a line of 8.5 centimeters, and for 1.2 meters per second I'd draw a line of 12 centimeters. So here first I drew the 8.5 centimeter line, and then using a protector you'd mark an angle of 45 degrees from the head of the first vector. After you've done that, you draw a line of the second line of 12 centimeter from the head of the first vector. Then you'd connect the first vector to the second vector by drawing a line, the resultant vector, from the tail of the first vector to the head of the second vector. And then you would measure the length of this particular line, which mine came out to be 8.7 centimeters, but here they want the velocity. So again you'd convert this into velocity by multiplying it with whatever scale you chose in the beginning, and that's 0.87 meters per second for me. Figure 2.1 shows two cars A and B before they collide. Car B of mass 1200 kg is stationary. Car A of mass 2000 kg is traveling towards B at 18 meters per second. So here you've got U of car A, where it has mass 2000 kg, and for B the mass is 1200 kg and initial velocity is 0, right? Calculate the momentum of car A. So the momentum again is equal to mass multiplied by velocity, and that will be 2000 multiplied by 18 is 3600. Don't forget the units, which will be kg meters per second. The cars collide and car B experiences an impulse. car A continues to move in the same direction with a momentum of 21,000 kg meters per second. Calculate the momentum of car B immediately after the collision. According to the law of conservation of momentum, the total momentum before collision is equal to total momentum after collision. Before collision, car B had 0 momentum, and so that means the total momentum before collision was the momentum of car A, which was 3600. Now after collision, the sum of momentum of car A and car B has to be equal to 3600. So that's what I'll write over here. 36,000 is equal to momentum of car A, which is 21,000, plus the momentum of car B, which we need to find out. And so momentum of car B is 36,000 minus 21,000, and this is equal to 15,000 kg meters per second. Determine the average impulse experienced by car B during the collision. So the formula of impulse is force multiplied by the time of impact, which is also equal to mv minus mu, or in other words, the change in momentum. Since we do not have the values of force and time during the collision, we'll go with this one. And initial momentum of car B was 0. That means impulse mv minus mu over here would be mv minus 0. And as we calculated over here, the momentum of car B right after collision is 15,000 kg meters per second, which will be equal to the impulse over here. The cars are in contact for 0.2 seconds, and calculate the average resultant force experienced by car B during the collision. Again, so we know that the formula of impulse is resultant force on a body multiplied by the time of collision. Since we now know the value of impulse, which is 15,000, we can find out the resultant force because we also have the time over here. And so force is equal to 15,000 divided by 0.2, and this is equal to 75,000 newtons. See, a modern car is designed so that during a collision, the front section of the car is crushed and the time of contact increases. Explain the benefit of increasing the time of contact for the people in the car. The aim of increasing the time of contact is to decrease the force experienced by people in the car, and that's because resultant force is equal to rate of change of momentum. As you can see, force and time have inverse proportion. They are inversely related to each other, which means if you increase the time of contact, you decrease the resultant force acting on the bodies. And so that's the case over here. You want to reduce the resultant force acting on people due to the collision, so that you would minimize the chances of injuries. Question 3. A test tube containing solid wax is heated by placing it in a beaker of very hot water for several minutes. The solid wax becomes a liquid. A. State in terms of molecules how a solid differs from a liquid. The typical distinguishing properties are the separation between molecules and their movements. So over here you can write how molecules in solids vibrate in fixed positions, whereas in liquid they slide past each other, and molecules in solids again are closely packed together, and they also have very strong bonds. B. Explain in terms of molecules why thermal energy must be supplied for a solid to become a liquid. Now, for a solid to become a liquid, it has to melt. So during this process of melting, kinetic energy of molecules remains the same, and temperature remains the same as a result of this. However, the potential energy of molecules increases so that attractive forces between molecules in the solid can be overcome. Thermal energy will be used to increase the potential energy of molecules, while their kinetic energy remains the same during this change of state while they melt. See, the test tube is removed from hot water and held in a clamp stand. Figure 3.1 shows the test tube and liquid wax cooling in air. So here you've got the apparatus. As the wax cools, the temperature is recorded at regular time intervals. Figure 3.2 is the temperature time graph for the wax. So here you've got a cooling curve in which the state of wax changes. During this region, since you're starting with wax in its liquid form, here you'll have liquid state. This is the duration where the wax is going to become solid. So here you'll have liquid as well as solid form of wax, and again the temperature drops, which means this one over here is just solid. So this stage over here is the change of state. Now as you can see, as the time increases, the temperature does not drop, the temperature remains the same. During any change of state, the temperature remains constant, the kinetic energy remains constant, and the potential energy will change. Now because it is a cooling curve, heat is being put out of the wax, that means the potential energy of wax will decrease. And after all of the liquid wax has converted to solid wax, the temperature will again start to decrease, and so the kinetic energy will decrease. Using figure 3.2, determine the melting point of the wax. Melting point is the temperature at which the liquid wax starts to turn into solid, and that's right over here, 57 degrees Celsius. So you write that down. The specific latent heat of fusion of the wax is 210 joule per grams. The test tube contains 50 grams of the wax. Using figure 3.2, determine the rate at which the wax is losing internal energy as the wax solidifies. Give your answer in joule per minute. Alright, the latent heat is equal to energy divided by the mass. So you've got the latent heat as 210 and the mass is 50 grams. You can calculate the heat energy by multiplying the two values, and that will be equal to 10,500 joules. Now you need to give the answer in joule per minute, so you need to find out the time that it takes for the wax to melt, because latent heat of fusion, it's related to the process of melting, right? So the amount of heat that you just calculated over here is the amount of heat that is being put into the wax while it is melting. So that means the process of melting is over here. This is where you put in 10,500 joules of energy. Now you just need to find the time duration. Here you have 8 minutes and this is 15 minutes. So 15 minus 8 is 7 minutes of time. You just divide 10,500 by 7, and so you will get the answer as 1500 joules per minute. Question 4. In an industrial process, a gas that is already at high pressure is trapped in a large cylinder by a piston. Figure 4.1 shows the gas, the cylinder, and the piston. The piston is pushed into the cylinder. As the pressure of the gas changes, its temperature remains constant. So Boyle's law states that pressure and volume are inversely proportional given that temperature remains constant, and this question relates to that law. Figure 4.2 shows how the pressure of the trapped gas depends on its volume. As the volume increases, the pressure drops. 1. Describe the relation shown by the graph between the pressure of the gas and the volume it occupies. Explain this relation in terms of molecules. Again, pressure and volume are inversely proportional to each other according to Boyle's law. As the volume increases, the molecules spread out more because they have more space, which this will reduce the collision frequency of molecules with the walls of the cylinder. Supposing we had initially 1 cm cube of volume and 3 molecules, right? And now compare this to the scenario of having 2 cm cube of volume and the same number of molecules. In the first situation, the molecules are more likely to collide with the walls of the container, and so this will create a greater pressure. Whereas in the second case, the molecules will take longer to collide, and this means the collision frequency in the second case is lower. And so if you increase the volume, you will decrease the pressure by reducing the collision frequency. To determine the volume occupied by the gas when it is released into the atmosphere at a pressure of 0.1 megapascal, you will need to use the data from figure 4.2. So you're given the pressure and you need to find the volume. According to Boyle's law, we know that PV, or pressure multiplied by volume, is constant, and that means P1V1 is equal to P2V2. So now you need to find the volume in second scenario, which means V2 is equal to P1V1 divided by P2. We know that P2 is 0.1 megapascals. You need to find any coordinate and plug its values of pressure and volume into this formula. So over here you've got 0.2 meter cube of volume and 1 megapascals. So this is the coordinate I'll be using. V is equal to 0.2 meter cube and P is equal to 1 megapascals, which means 1 times 10 to the power of 6 multiplied by 0.2 divided by 0.1 times 10 to the power of 6. And this comes out to 2 meter cube, which makes sense because you are going to reduce the pressure from 1 megapascals to 0.1 megapascals. So the volume is going to increase. B, an unused cylinder of the compressed gas is moved into a cold warehouse. The temperature of the gas decreases. State how the decrease in temperature affects the motion of the gases. Because the temperature increases, the gas molecules will slow down because their kinetic energy will decrease. To the pressure of the gas in the cylinder. According to pressure law, pressure is directly proportional to the temperature of a gas, and so that means if temperature is decreasing, the pressure will also decrease. Question 5a. Radio waves, ultrasound, and visible light are all waves. 1. State what is meant by ultrasound and suggest a value for the minimum possible frequency of ultrasound. Ultrasound is any sound wave of a frequency that is greater than the frequency which is audible by the humans, right? So this is any frequency of sound which is above 20,000 hertz. To state which of the waves are electromagnetic. So visible light and radio waves are both part of the electromagnetic spectrum. So I'll write that down over here. And ultrasound is a longitudinal wave. B. Ultrasound passes through both human flesh and bone. Figure 5.1 shows an ultrasound source sending an ultrasound wave into human flesh. The ultrasound wave travels through the flesh to point X and then through the thickness of the bone to point Y. At Y, some ultrasound is reflected and returns to X. The total time for the ultrasound to travel in the bone from X to Y and then back to X is 9 times 10 to the power of negative 6 seconds. The speed of ultrasound in the bone is 4,100 meters per second. Calculate the thickness of the bone. Now you're given with the speed, you are given with the time, and you need to find out the distance, right? So the formula of speed is distance divided by the time taken. Now this time is the time taken that it takes the ultrasounds to travel from X to Y and then back from Y to X, which means this is the time taken for 2 times the distance or 2 times the thickness of the bone. So that means the time taken for the ultrasound to travel from X to Y in one direction, or the time taken to travel the thickness of the bone, will be half of this. So you divide 9 times 10 to the power of negative 6 by 2, which is equal to 4.5 times 10 to the power of negative 6. Alright, so here you have your time. Now distance is equal to speed multiplied by time, which is equal to 4100 multiplied by 4.5 times 10 to the power of negative 6, which is equal to 0.018 meters. Question 6a. A block is made from a particular type of glass. Figure 6.1 shows light passing from air into the glass block. Using information from figure 6.1, calculate the refractive index of light in this type of glass. When light waves travel from a less dense medium to a more dense medium, the refractive index is equal to sine I over sine R, where I is the angle of incidence and R is the angle of refraction. Angle of incidence would be the angle between the normal and incident ray. So here you've got the angle of incidence, which is going to be equal to 90 minus 29, and so this will be 61 degrees. If you're confused as to why that's 90 minus 29, it's because you have between the normal and the surface of the glass, the angle is 90 degrees, and so to find out this particular angle, you'd subtract from 90 the value of this angle. Okay, and the angle of refraction is 33 degrees, so this would be sine 61 divided by sine 33, and this is equal to 1.61 corrected to 3 significant figures. To find out the critical angle for the light traveling into this type of glass. Now refractive index is equal to 1 divided by sine of critical angle. That means sine of critical angle is 1 divided by n, and so critical angle is sine inverse of 1 divided by the refractive index. So C is equal to sine inverse of 1 divided by 1.61, and this will be equal to 38.4 degrees. B. State one application of optical fibers and draw a diagram that shows how an optical fiber is used in this application. So you can give any proper example over here. In my case, I'll be using telecommunications as an example. Let me just give a brief overview of how they function, or the mechanism of optical fibers. The optical fibers use total internal reflection to perform their functions, and this happens when the angle of incidence in the denser medium is greater than the critical angle, and this will cause all of the light to reflect instead of refracting. So here is my drawing of the optical fiber. Light is going to enter, and because we'll see in total internal reflection, none of the light will be refracted, all of this will be reflected, which means the angle of incidence will be equal to angle of refraction. Again, once it strikes the surface, it will be reflected, and this will continue until the light exits. So I'm drawing labels to point out the direction of light, and my answer will include the example of telecommunications. Question 7. A lightning conductor protects a tall building and the people in it against damage and injury caused by lightning strikes. The lightning conductor is a very long stripe of copper that is attached to the side of the building. At the top of the building, the stripe of copper is connected to a vertical metal pole, and at the bottom of the building, it's buried in the ground. Figure 7.1 shows a thundercloud passing over the building. The bottom of the thundercloud is negatively charged over here. As the cloud moves closer to the building, the top of the metal pole becomes charged. A. State the sign of the charge at the top of the metal. Explain in terms of the particles involved how it becomes charged. So here you've got negative charges, right? This means it will repel the electrons in the metal pole to the ground, and so the metal pole will become positively charged. B. As the cloud passes over the building, a lightning strike occurs and a charge of 0.84 coulombs flows through the lightning conductor. The charge flows for 3.5 times 10 to the power of negative 5 seconds. 1. Calculate the average current in the lightning conductor during this time. So current is equal to the charge divided by the time, which means you've got 0.84 divided by 3.5 times 10 to the power of negative 5, and this is equal to 24,000 amperes. You will be writing this in standard form. 2. It is suggested that the current in the lightning conductor could be measured by connecting a laboratory ammeter between the pole and the copper stripe. State one reason why this cannot be successful. So laboratory ammeters are only suitable for small amounts of readings of current. So if you were to measure this amount of current using laboratory ammeter, it would get damaged, which is why it's not possible to do this. C. The copper stripe has a large cross-sectional area. State how increasing the cross-sectional area of copper stripe affects its resistance. Now resistance is equal to the resistivity length multiplied by length divided by the cross-sectional area. As you can see, cross-sectional area and resistance of a conductor are inversely proportional. So if you increase the area, resistance would decrease. Question 8a part 1. In the space below, draw the symbol for a NOR gate. This is a combination of NOT and OR gate. To complete the truth table for a NOR gate. For an OR gate, the output is the opposite of what you'd get from an OR gate. So that means you'll get 1, 0, 0 and 0. B. The fuel for an engine needs to be warm in order for the engine to work. If the temperature of the fuel is below the working temperature, an LED emits light. LED is over here. This is a light emitting diode which will light up when current flows through it. Figure 8.1 is the diagram of the circuit that includes the LED. Component Y is in the thermal contact with the fuel. 1. State the name of the component X and the name of the component Y. X is a variable resistor, also known as a rheostat, and Y is a thermistor. Now thermistors are sensory resistors, and the resistance of a thermistor depends on the temperature, and they are inversely proportional, which means as the temperature increases, the resistance of a thermistor would decrease. Now, if the temperature of the fuel is below the working temperature, that means if the temperature decreases below a certain value, that means the resistance of the thermistor is going to increase, right? Now, if the resistance increases, that means the potential difference across the thermistor would also increase, because according to Ohm's law, potential difference is directly proportional to the resistance. Now, if potential difference across thermistor increases, that means the LED will light up. 2. The fuel is too cold and the LED is emitting light. State and explain what happens in the circuit as the temperature of the fuel increases to a value above the value TW. Now, as the temperature increases, the resistance of the thermistor is going to decrease. Alright, now that means if the resistance of any component in a series circuit decreases, the total resistance decreases. So the resistance will decrease, and as a result of this, the current in the circuit will increase. Current through all of the components in a series circuit is the same. However, because the resistance of Y or the thermistor is going to decrease, that means the potential difference across the thermistor and the potential difference across LED is going to decrease. And because thermistor is connected in parallel to the LED, the potential difference across both of these components is going to be equal, which is why when the potential difference across Y decreases, the potential difference across LED will also decrease. So V across Y will decrease, and so that means V across LED will also decrease, and this means the light will go out. See in figure 8.2, the LED is now in parallel with component X instead of component Y. So now the LED is connected in parallel with the variable resistor. The temperature of component Y increases from a value below T to a value above T. So once again, I'd draw the temperature resistance graph to help myself. Predict what happens in this circuit, suggest a value for the circuit, a use for the circuit. Now we're told that the temperature is going to increase. That means the resistance of the thermistor is going to decrease. Once again, this means when the temperature increases, resistance across the thermistor decreases. That means the potential difference across the thermistor will decrease, across Y will decrease, which means a greater share of the total EMF or the total voltage is going to be provided to X. Now that means if the potential difference share of X increases, the potential difference of LED will increase because they are connected in parallel, and so they have the same potential difference. And as a result of this, the LED will light up. My example over here would be to use this circuit in, for example, an electric kettle, where the LED will light up when the temperature of water reaches its boiling point. Question 9. The two ends of a metal rod are connected by copper wire to a very sensitive ammeter. The rod is placed in the horizontal magnetic field between the north pole and the south pole of a permanent magnet as shown in figure 9.1. Alright, so you've got a conductor placed in a magnetic field and it is going to be moved. The rod is moved at a constant speed in the direction shown by the arrow in figure 9.1. So it's going to be moved perpendicular to the magnetic field lines, which are going to be pointing from north to south, and you are moving the metal rod, which is going to be a conductor, in a direction that's perpendicular to the magnetic field lines. And this means an EMF will be induced in the rod. An EMF is induced in the rod. One state two factors that determine the size of the induced EMF. This can be the velocity at which the metal rod is moved, the magnetic field strength of the magnets, and also the length of the metal. 2. The size of the current in the ammeter depends on the size of the induced EMF. State one other factor that affects the size of the current. Now, current in a conductor is equal to the EMF or the voltage divided by the resistance. That means the current also depends on its resistance or the resistance of a conductor. Now resistance again is equal to resistivity multiplied by length divided by area, which means you can mention any of these factors. And again, area is cross-sectional area for a conductor that's in the form of a wire is pi r square or pi d square by 4. So you can even mention the radius and the diameter of the conductor. 3. The direction of the motion of the rod is now changed. It moves at a constant speed towards the north pole as shown in figure 9.1. State and explain what happens to the induced EMF. Now, as you can see, you've got the field lines that are parallel to the motion of the conductor. Now, the conductor does not get across the magnetic field lines, which is why EMF will not be induced, because according to Faraday's law, EMF is only induced when the conductor moves across the magnetic field lines and not along them or parallel to them. B. Figure 9.3 shows a rectangular coil of wire placed in the same horizontal magnetic field. So that's between the two magnets. The coil rotates in the direction shown by the arrow in figure 9.3. This is a rotation in clockwise direction and EMF is induced in the coil. Sketch a graph to show how the EMF varies with time for 2 complete revolutions of the coil. You draw a sine curve and 2 complete cycles of it, because you need to show 2 complete revolutions of the coil. I'd suggest using a scale here to ensure that the heights of all of the peaks is equal, because the magnitude of EMF that is induced should not be different in the cycles. which will ensure that you score both of the marks. 2. On your sketch in figure 9.4, mark a letter T to indicate a time when the coil is horizontal as shown in figure 9.3. Now when the coil is horizontal like that, it is going to be cutting the maximum number of field lines, which means a maximum amount of EMF is going to be induced, right? And so that is going to be at a time when the EMF peaks. So this can be this particular time or this time, any of them. The EMF can be positive or negative, doesn't really matter. It has to correspond to a time where the EMF peaks. A sample contains atoms of a particular isotope of protactinium with the mass number X and proton number Y. A nucleus of this protactinium isotope contains 91 protons and 143 neutrons. State the values of X and Y in the symbol, in the chemical symbol of protactinium. So again, X is the mass number, which is going to be equal to the sum of proton number and number of neutrons. So you'd add 91 to 143, which is 234, and Y is the proton number, which is 91. 2. This isotope is radioactive and it decays by the emission of a beta particle to an isotope of uranium. Complete the equation for the decay of a protactinium nucleus. So you start by writing out the mass number and proton number of the starting element, which is 91 and 143. As a result of beta minus decay, the nucleon number remains the same. However, the number of protons increases by 1. And so in this equation, the charge and nucleon number is conserved. When you add 92 to -1, you get the same number as you have on the left hand side. B. A radiation detector measures a background count rate in a laboratory of 32 counts per minute. Suggest 2 naturally occurring sources of background radiation. This can be rocks and the sun. 2. The sample is placed in a laboratory close to radiation detector and the count rate increases to 544 counts per minute. This isotope of protactinium has a half-life of 400 minutes. That means it takes 400 minutes for the amount of protactinium to become half of its original value. Predict a value for the count rate measured over 1200 minutes later. So I'd like to see how many half-lives have passed in 1200 minutes. So you divide 1200 by 400, which means 3 half-lives. Now this count rate includes the background radiation as well. So to find out the count rate due to protactinium only, you'd subtract 32 from 544, and that is going to be equal to 512 counts per minute. This is the count rate due to protactinium. The count rate is how much radioactivity is detected in a certain amount of time. In our case, it's in a minute. And this depends on the number of radioactive atoms that are remaining. If you want to find out the count rate after 3 half-lives have passed, that means you divide 512 by 2 cubed. And that's because you have 3 half-lives that pass in 1200 minutes, and in each half-life the number is going to be reduced by 2. So there's that, and this will be equal to 512 divided by 8, which is 64 counts per minute. Now this is the count rate due to protactinium, but you need to find out the count rate which is detected by the radiation detector, and it is also going to detect the background radiation. So you'd add 64 to 32 as given in the question, and this will be equal to 96 counts per minute. 3. Suggest one reason why the count rate measured over 1200 meters later may differ slightly from the value predicted in B. And that's because count rate fluctuates randomly, so it may differ. Alright, that is it. We are done with this paper. Thank you for watching.